Welcome students to the week 4 and our continued lecture series on the R statistical programming language. I just wanted to give you a word of encouragement as you try to tackle R. I can't express to you how significant the R significant language has become in the analysis of next generation sequence data. And but I also know that it is difficult language to pick up and to understand, and so I'm really trying to establish here in these few introductory lectures really a foundation that's going to allow you to understand R sort of from its core, and not give you sort of a glossed over version of or introduction to the language. And so I just thought I'd start by briefly hitting what I thought were some of the more important points from the week 3 introductory series on R. And then, we're going to take it a little bit slow and not try to learn too many of the more sophisticated methodologies that are available with R, but just give you some of the basic skills that you'll need to really scale up to larger, if not very large, data sets. So again, this is these first 3 or 4 slides are just a review of points that I thought were very important and that I want to reiterate. One is that these conditional operators, okay, so we can they allow you to identify sort of on an element-wise basis when evaluating a vector as to whether or not a particular element of the vector meets a particular condition. So if we have a vector here of values of 1 to 10, which we can specify in either of these two ways, we can then ask, well, which values in this vector are greater than 3, and what will be returned by R to this variable I'm calling here is.gt3 is a logical vector. Okay, that's just a series of trues and falses as to whether or not the corresponding positions in the query vector here are true and false. That is, are they greater than 3? Obviously, this is similar for a different condition, and these are the different numerical conditional operators we can specify when we're evaluating a particular condition. So one interesting property then is that when you use the sum command on a logical vector, you end up summing the true values. So this is an important concept once again. We can also subset a vector based upon that conditional, the logical vector that's returned by this conditional operation. Okay, and what that returns then is only the elements that evaluated to true in the original vector. So we're taking numbers. We have a series of trues and falses in the is.lt5 vector. And what that will do is subset the numbers vector for only the elements that are true in the is.lt5 logical vector. And here I'm just then assigning that new vector, which will be truncated and will consist of less than 5. So it's 1, 2, 3, 4. And we're assigning that here to the LTEQ5. For lack of a better name for the variable. We can also do the string matching this way, and find ways to simply count certain strings, say, that are in a vector, such as nucleotides. Just also something to keep in mind here: the double equal symbol is the same in R for string equality as it is for numeric equality. Okay. So that was one point that I thought was important. I guess I could go ahead and blow this up here for you. another point is the subsetting of a data frame. Okay, so this is a skill that I think is one of the things I would like for you to take away from this course, because it is a very important skill that allows you to basically slice and dice a very large data set, okay, which sometimes you can't even read into something like Excel. And oftentimes, however, as bioinformaticians, we're not interested in using something like Excel, which in principle can do many of the same things, and yet what we're trying to do is build software that allows automation of analysis in many cases, so reusability. And R provides a lot of tools for doing that. So here we can do some simple things. I introduced these concepts anyways. We can subset it based on a column or row name. So here's the name of the data frame, and here is, remember, when you're subsetting data frames, where values to the left of the comma are the specifying rows, values to the right of the comma are specifying columns. You notice that the rows have no values here. That's implicitly means all rows for column A. Okay, the column named A. Okay, so that's how you extract a column from a data frame based on its name. Sometimes you don't have names on columns and you just know numbers. You can do the same thing. Let's say you wanted column 1, just get rid of the name here and replace it with column 1. So you'd have blank column 1 would extract the first column. Now, more importantly, this is fairly straightforward. More importantly, we often want to subset based on conditions, right? So now we have to write some code here to extract the columns or rows that we want based upon some conditions. So let's say we want, I've made up a column here called positions, or pos, in the D frame data frame, and what we want is positions. Positions here might be like a coordinate on a chromosome. So maybe we want all positions greater than 10. Simple. Notice here that this is extracting a column. Let's break it down. This inside the brackets, okay, we are extracting a column just like here, okay, except a column like position. But we're extracting based upon a conditional operation which returns a logical vector, as I showed you in the previous slide. So here we're going to get a set of values, trues and falses, as to whether the column position contains a value greater than 10 would evaluate to true, anything 10 or less would evaluate to false. So that gives us a logical vector. So we're passing in a logical vector to this sort of subsetting or indexing operation we're doing, and notice the comma. So what we're saying is we want rows here that evaluate to true, right? And given that we developed our conditional operator based upon the positions column, that means that we'll be extracting all rows in which the positions column is greater than 10. Okay. Notice here that implicitly we are saying we want to return all columns. In other words, we're not deleting columns here in this subsetting operation. Okay, and of course we're subsetting the original data frame, which I've called here D frame. Okay, so hopefully that helps you a little bit. Just as a refresher, again, this is really essential. I have you doing it again, working with this a bit some more in the week 4 homework, as you have hopefully started in the week 3 homework. So here I reiterate this point. Finally, we can subset a data frame based on position. I gave you the example up here of extracting column 1, but we can also extract any set of rows and columns we want. We don't just have to specify one value. Just like here, we specified an entire vector of trues and falses. Here we can specify an entire vector of index positions. So this is going to extract to the left of the comma is rows, to the right is columns, the first 10 rows, and the first 3 columns. So I did also mention in the week 3 lectures the idea of these what are called logical operators. Okay, this is a way of combining logical statements, okay, and asking what positions in 2 vectors both evaluate to true for whatever condition, or simply in a logical vector comparison, which are the positions that are true in both vectors. And or here, which says which positions have a true in either or the other of 2 logical vectors we're comparing. What this allows you to do is to make complex queries, okay, of data frames in many cases, or lots of other contexts, but you can combine sort of 2 conditions, okay? Remember, the conditions return logical operators, these conditionals like greater, less than, greater than or equal to, etc. But we can combine 2 sets of conditions, say here, greater than numbers greater than 10 and numbers less than 25. So we can subset, just returns a logical vector, okay, of the same length of the initial 2 logical vectors, okay, simply though evaluating which of the positions evaluate to either both being true in each position in case of the AND operator, or here one or the other being true. Okay, so this, hopefully you can see here, we're just subsetting a vector. We know that because obviously there's no comma. So we can subset a vector the same way we do a data frame, simply it's one-dimensional. So again, we're just subsetting those positions in the original vector that evaluate to true in this logical, okay? Which is obviously the logical here, because of how we defined it, starting with the numbers vector, is the same length as the individual numbers vector. So only then we are extracting the values that evaluate to true, okay, in this sort of shorthand here, where we're not taking the intermediate step of defining sort of an additional vector here. We're just going ahead and defining the vector or this logical vector directly. Okay, I understand that this can be difficult to grasp quickly. That's why I'm kind of wanting to pause, take a little bit slow, because these are points that I think form the foundation of understanding R, at least for the applied analysis of large data sets. This is going to allow you to develop the skill you need to take a very large data matrix and quickly dice it, and then automate the analysis, which in many cases you need to do, because you need to repeat the analysis many times with different conditions, different settings, etc. And this, in the R statistical programming language, gives you sort of the ability to do that. Okay, let's jump to a new topic here. There's really only three short topics I want to introduce today. One is loops. One is conducting simple statistical tests. We're really just looking for examples here because this is not a statistics course. And then I'll talk briefly about some of the graphing techniques that you may have tried in the week 3 homework, which I kind of wanted you to just read some documentation and kind of see how if you can figure it out with the tips that I gave you in the homework. But I'll just show you more formally here how some of that plotting works. So loops are really important. If you have done any programming, you know a lot about loops. R has many of the same loops as do other common scripting languages, and loops allow you to do repetitive operations. So let's say that we had a list of RNA-seq data, sort of a massive data frame of RNA-seq data where we have some, difference in the number of read counts between two treatments. And we want to do a statistical test on every single gene in the genome. So every gene, we have the gene identifier, and then two additional columns, one that has the read count in treatment 1, and then another that has a read count in treatment 2. And we want to know, are these statistically different, or at least what's the difference between the two counts? We would, of course, need replicates to infer statistical significance. But in any event, what you can do is you can loop through then every gene in the genome and conduct whatever, calculate whatever statistic or p-value, etc., that you want to do for it on a gene-wise basis. Okay, but somehow you have to, take a lot of data and sort of loop through, iterate over, each gene. So how might that work? Well, the for loop is one way to go. Actually, R offers a lot of ways to go here, but for loops are common and generalized across languages, so I thought I'd give you an example. Here's I in 1 to 10. This is sort of the R way of doing it. The I really here is sort of a counter in this case because we have numbers here. But what will happen to I is that each time through the loop, I will be reset to the next value in this, what I'm calling the loop vector here. Okay, so this is values 1 to 10. The first time through the loop, I will be a value of 1. The second time through the loop, I will be a value of 2, okay, etc. The loop will continue until it's reaches 10. It will enter the loop on the 10th time, and then it will exit the loop once it's completed the 10th iteration. Okay, so why don't you go ahead and type this in. In fact, maybe for this example, I'll go ahead and do it for you, just because I also wanted to show you that in this case, like, we're dealing with multiple lines of code, right? Most of what we've been doing so far is simple one-liners in R that can be entered at the command line. But when you start dealing with loops, it really is helpful to start writing R scripts. So in RStudio, you can do that simply by opening, here, this R script, you can go to File, New R script. That's one way to do it. The other way is to just take this shortcut right here. So let's go ahead and just quickly type in this loop so we can see what happens. So what happens is that these curly brackets here represent the sort of the block that gets iterated over and over again. So everything inside the block, okay, gets repeated for each time through the loop, or each iteration. So here we love NGS so much, and then we do fill equals true. With this cat in this context, so cat in R anyways, is really just similar to print or echo. So it's a way to echo, to kind of the standard out or to the terminal text. You can also use it to concatenate text. That's not really the point here, but this allows you to track easily what's going on. Fill equals true means add a hard return or add a end of line character that causes a new line after the cat statement. So not to worry there. So let's see what happens. Okay, so to do this, what I'm showing you here is another technique in the RStudio. I'm not sure if I showed you this in the last lecture or not, but you can just highlight here the block of code you want to run. Okay, so we can highlight the entire loop, including the closed curly bracket. We can run it. and here it printed to the terminal here, I love NGS 1. Okay, I love NGS 4. So here what I'm doing is I'm printing the variable I times itself. So the second time through the loop, I is 2, so 2 times 2 is 4. First time through the loop, I is 1, 1 times 1 is 1. Third time through the loop, 3 times 3 is 9, 4 times 4 is 16, etc. The last one should be 100. Here it is, I love NGS 100. So we're simply doing an operation here inside the loop and showing you, kind of how the loop works. Okay, hopefully that's clear. Watch the video again if it's not. So let's go back here to the slideshow. So once again, the curly brackets define the loop block. And this final tip here is that these are multi-line sort of programming code, and so you really need to write these down in some kind of script in order to write coherent code. You generally don't execute loops just by typing one-liners at the command line, although it's possible. I recommend writing it down in a script. In fact, I recommend writing most everything you code up in a script, other than quick and dirty things that you want to do at the command line. So, just to be clear here, we can, sort of change our protocol of how, we're iterating. This is, again, just a numeric vector, 1 to n row, which is the number of rows in a data frame. So here what we're doing is we're iterating effectively over the index positions of the rows. So here I begins at 1, which in this case would be, say, the first row of this data frame. And here maybe what we want to do is extract row I, column A. Okay, so here we're subsetting dframe for the position on the left is the row. Here we're using combining sort of an index position and a name. That's fine to do. This is a typo. I'm sorry about that. This should be a small I here because that's the variable here that's being modified each time through the loop. So I is changing. The first time through the loop, we're going to subset row 1 and column A here, assign it to this variable, and here we're going to extract row 1, column B. Next time through the loop, row 2, etc. This time we're going all the way to the number of rows. So here we're not having to, predefine how many rows are in our data frame. We can make it more generic and use this so that, say, if we're reading different size data frames in different sort of in our program, we don't have to know the size ahead of time. Okay, we can. This is a way of generalizing your code. So most of the time we want to store some values that we calculate each time through the loop. Okay, so let's imagine we have a vector here 4, 9, and 16, and we want to calculate the square root of each value here. Okay, I'm being a little bit taking liberties here to illustrate the for loop. I just want to be clear to all of you that R is what's called a vectorized language, so we can actually do this without a for loop, right? These simple operations here that I'm just using to illustrate are really just illustrations, right? We can just type the square root directly, and remember, because R works in a vectorized fashion, it's going to calculate the square root for each value in the vector. So you don't actually have to write a loop, just want to be clear about that, but it just gives us a jumping off point here we can write it with a loop, certainly. Let's do that, right? So here we have numbers. Here what we want to do in this example is store the values from the square root of these numbers in a new vector called storage. we can iterate over here, again making generalizable code. We can say 1 to the length of numbers. We could just say 1 to, and colon 3 here, but this makes generalizable code. And then what we can do is calculate the square root for the current number. Okay, so remember, I is being modified each time through the loop to be 1, 2, then 3. Okay, because we start with 1, and the vector we've used here as our loop vector is a set of values 1 to 3. So first time through the loop is 1, so we index the numbers vector for position 1, which is a 4. Next time through the loop we'll index position 2, which is a 9. The next time and final time will be position 3, which is a 16. We calculate the square root sort of individually on each number each time through the loop, save it to square root. And now the trick here that I wanted to show you is what we call growing a vector. And we can use the append function. I'll leave you to type help append at the command line so you make sure you know what the append does. All it does is it tacks on the value square root to what currently exists in the storage vector, which initially is just an empty vector, and then we resave storage. Okay, so we overwrite the storage vector by writing our pointer here, by reassigning this value to storage, which clears storage of what it previously was defined as. Okay, so each time through the loop we'll be modifying storage by adding, using the append function, the additional square root value. Okay, in the end, I'll let you think about it and type it into your R script and execute it the way I just showed you. And if you execute this small piece of code, you will get the result 2, 3, and 4. Okay, for the square root of these values. All right. This is a bad idea. I actually, it is quick. It is the fastest way to store values. But it's not always a good idea. In fact, so disclaimer, I actually have you in the homework do this growing vectors because it's simple, right? I want to try to keep things as simple as possible for you as you're learning R. But it's a bad idea because tacking on, for whatever reason in R, it has to do with memory consumption. R does not handle this operation well, so when you scale up to millions of these append operations, it becomes very slow to do it that way. So the better way to do it is to fill in values. Okay, this is just a heads up. Don't worry too much. I certainly won't quiz you on this, so I'm not gonna probably even won't get to the point where I put this in a homework. But it is an important consideration when you're working with large data sets, so I did want to mention it. And so the repeat function here, or rep, is the repeat function. We can repeat an NA 3 times. So storage starts out as a vector of 3 NAs, or not available values. Right? So here now we loop through these 3 numbers, we calculate the square root like we did before, but notice what we do here. Here, for the first time, I'm showing you a way to assign a value to a particular position in a vector. So we're looping through the values 1 to 3. This is a typo. I'm sorry about this. I didn't, it's funny here. This should be 1:3. Sorry, just like it is here. I apologize for that. So I in 1 to length numbers here is, first time through the loop is 1, second time through the loop 2, third time through the loop 3, and here we go. What we do is we now assign to the position I, which is 1, 2, or 3, depending on the time through the loop, the square root, which is the value we're calculating for each of these numbers. Okay, so we're using I here to both index the numbers vector and also assign to the storage vector, which is predefined in its length. Okay, this is what we call filling in. So we're going to overwrite, in the first time through the loop, we'll overwrite the first NA in this storage vector. Okay, we're going to overwrite it. what the end game here is that by predefining the length of this vector as a and keeping it, starting it with its full length, that is saves a lot of memory, and it is a much less intensive operation for R. So this only matters in very large data sets, which is why it doesn't matter on your homework whether you use this filling in approach or this growing approach. But anyways, this also illustrates this additional point that we can assign a value to a particular position in a vector using this type of notation. It is the first time that we've used sort of a position to the left of the arrow. Okay, the assignment arrow here. We are not going to talk about other types of loops in this class, but you can use the question mark control to identify in the help other control structures or loops, or what are called flow control structures, like while loops, repeat loops, do loops, things like that. And then I'd also mention something that we probably won't have get into, because this is a sort of the next level of difficulty in R. It's not essential in most cases, but it really makes life easier, especially when you're working on large, complicated data sets. The apply family of functions allow you to iterate over rows or columns in a table. They allow you to do a whole variety of things in the most efficient way possible, and I'll just leave it at that. But those of you who go on and someday come back and revisit this lecture, the apply series of functions is something that maybe we'll have a chance to sneak it into homework or something we're doing later on. But for now, we'll try to keep it simple. So let's jump quickly to statistical operations. I don't want to spend a lot of time here because I really just want to illustrate what how it works generally. I think I've shown you this, but maybe not in detail. But all R norm here, and you can do this with many of the standard distributions in statistics, is you can just draw a number of samples from a distribution here that I've defined with a mean and standard deviation of 1. Okay, so this defines sort of the normal distribution. Here we can sample randomly from that distribution and draw values out of a distribution with a mean and standard deviation of 1. The t-test, as many of you know, is simply a test to compare the means of two samples. So let's say that we want to compare the heights of individuals living at the North Pole versus individuals living, on the equator. And we can test sample 1 and 2 with what's called a t-test, which assumes normality of the underlying samples. But here I'm just creating a data set from scratch, illustrating a point of how you can generate normal or sample normal distributions to generate a normal sort of data set. And here we use the mean 2, so these are going to be different in a t-test because our sample size is large and because there's a large difference in the mean. And here, all it is, to conduct the test in R is t.test, sample 1, sample 2. You can read the documentation on t.test to learn, about the test a little bit more. But we get a result, and this is the point I wanted to make. You end up with a result object. Okay, and this object has data elements or elements of the result that we can extract if we know what the sort of named element is in the result object. Okay, that sounds a bit complicated, but it's not, and it's really meant to just provide a means for you to easily extract the values, not to make it complicated. So how do we know what values are in this result object? Well, we need to go to the t.test documentation, and if you go to the value section, I'm giving you some detail here because I have you do this in the homework for the Fisher test. But for the t-test, if you go to the value section of the documentation, you will see statistics, parameter, p.value, and other things listed in the value section. what we can do is use result dollar statistic to extract, in this case, the t statistic, result dollar parameter, which is the degrees of freedom in this case, and result dollar p dot value, which is the p value or the significance of the test, okay, or the probability that the null hypothesis is true. So this dollar symbol I've shown you before. It's sort of in our sort of shorthand for accessing a named component of some variable. Okay, so in any event, you don't need to know any more than that. This is how you go about extracting the individual sort of values from the result. If you just type this without and enter this at sort of your command prompt without assigning it to a result variable, you end up getting a printout of the results, which you can is sort of readable right there at your terminal. So it prints or writes right there to the R command prompt terminal. Okay, but what this allows us to do is then to begin to automate, because we're capturing individual results, which allows us to dump them, say, to a table for, say, 100,000 times we want to do this test for many data sets. Okay, we can do it many times by writing a loop, conducting the t-test, extracting the p-value and what other values we want, and writing them however we want, say, into a new data frame, and then writing that data frame to an output file. Okay, here's another example. I really don't, mean anything more than to illustrate sort of a practical example that you frequently will run into large next-generation sequence data sets. Here we have, and we will come back to this later, the statistics here are not so important as the implementation of the statistics, but frequently we want to know what in a set of genes where we know that what we want to know is whether or not a particular functional term is enriched, okay, in a particular RNA-seq data set. So where we've identified genes that are differentially expressed, and we want to know, whether a focal Go term or gene functional annotation type, say, metabolic enzymes, tend to be differentially expressed in light versus dark treatment of some cell type or yeast, say, for example. And we want to know if the Go term is enriched, which Go terms are enriched. And so what we want to do is we want to conduct this analysis essentially on all Go terms, which could be thousands. And so this is the way you would do that. Notice here that for a 2x2 contingency table, we input a matrix, okay, into the chi-square.test function. It requires a matrix. A matrix is simply a vector. Notice the values 172, 63, 62, 64, 6701 here in a linear vector, but then we just apply a dimensions to the vector. Okay, and so what this gives you is a 2x2 table that looks essentially exactly like this, because it's got 2 rows, 2 columns. It fills by column, meaning 172 and 63 are in the same column, 62, 64, 6701 are in the second column. I'll let you try this out. I encourage you to try it out. And again, what we can do is do the test, input matrix, we get a result object. We can, extract the values that we want. Again, you can look at the chi-square.test documentation to know, which, sort of compartments of the result object, are named so that you can extract them using this syntax. Okay, let's jump to our graphics. You can produce, graphics in many formats. That's important. You can do it on your screen or what's called the graphics device, which, here is this, in RStudio anyway, is plots. This is one good reason to use RStudio, because sometimes if you don't have it, it's not clear what the plotting device is. If you're just working from the terminal, here it's clear the plotting device is right here. We can easily plot on the y-axis 100 values from the normal distribution, and on the x-axis we can plot just continuously 1 to 100. Excuse me, this is the x-axis here. The first entry is x, the second entry is y, and this is the plotting device here where the graphic appears. Oops, sorry about that. Let's go back here to our lecture here, and we have PDFs. We can print right to those. That's convenient. JPEGs, PNGs, virtually any format we can create from R. R is built now for handling graphics and outputting in different sort of formats, which is important for generating publication quality graphics, where many publishers, for example, actually need different formats. So we typically design the graphics on the device that I just showed you, and then once we have the graphics sort of finalized, then we plot to a PDF. Just a heads up to some of you, Ubuntu has, RStudio, I have had some problems getting PDF function to work. So this is how in your script, before you call, say, plot or whatever plotting function you're using, you would type PDF. This is a function that has an argument, which is the name of the output file and some dimensions. Okay, and if you call that before executing your plot command, rather than writing the output to the plotting device or the graphing device on screen, what R will do is export that graphic to a PDF and render the PDF so that you can open it as you would any other PDF file. So again, the series of commands is PDF. Then your plot commands go here. Then you can turn off the connection to that PDF, which is becomes the current device by using the dev.off command. Just a quick thing about configuring your layout. There's this function called the par, okay, which are plotting parameters, which you specify before you begin plotting, similar to the way you would do PDF. But here, this MF row simply means that we want to plot that the next 4 plotting commands that are called that write to the open device, okay, will appear, on the same device. Okay, so we can do a 2x2 matrix of plots. Okay, this allows us to create 4 plots on one device. So we can 4 plots on one PDF. We can plot 4 plots, to our device here. So just a quick example. Let's first do dev.off to show you we can turn that graphic off that way. And now what we can do is let's do par. In fact, oops, this is a vector. Sorry. Okay, and then what we can do is plot, say, something simple here. We can then create a histogram from a series of numbers. Maybe draw from 1,000 numbers from the normal distribution here. These are all just defaults, which don't look very pretty, to be honest, and it's sometimes a bit frustrating that the defaults aren't. Let's just create something here where we create a bar plot. We can give it a little bit of color. Okay, and then the other common thing to do maybe is a box plot for these simple types of plots. Let's do rnorm with 1,000 points with the default, which is the mean of 0, standard deviation I think of 1. We do our Poisson, which allows us to draw from a Poisson distribution 1,000 values. Let's give it a lambda value of 2, which we have to specify. And here you can see the box plot appears here. So this was par MF row.
This allows us to, create however many plots in whatever fashion we want. Notice the row part, meaning it filled by rows. It did this plot first, then it went to the right, filled this, and then it went to the second row of plots, so to speak. Anyway, hopefully that gives you some idea. That was just quickly, what I wanted to illustrate really with these plotting basics. Here. So you can review this if you want, but I just basically told you everything there at the R command prompt that I wanted to illustrate here. Don't worry too much about these formula methods. Just another way of actually issuing plot commands, particularly when you have factor levels. You can do very complicated plots with very simple commands in R. Just a heads up that you have different kinds of plots. Just by using plot with the type equals H or type equals L or type equals N, which means suppress the plotting. This is a feature rich. So this is a skill you can learn over years about how to use these R plotting functions, but here's some of the more common ways of modifying a plot. And we won't go into too much detail here. Maybe later in the course we'll play around with generating more complicated plots simply to show you the flexibility and the professional quality of the plots. But I would say a huge percentage of the plots that are now being generated from next generation sequence data are generated in R. So that was actually where I wanted to end this particular lecture. So I think I ran a little longer than I wanted to, but hopefully just the review and keeping it simple, not introducing too many new concepts here, will increase your skill set and help to reinforce some of the things you already know about R. Okay, so we'll see you again next time.